Hello everyone, I'm Suresh Kumar Maddala. Today I'm going to present what are the advantages of AutoML and how AutoML is transforming predictive analytics with 60 to 80% of faster development. I'm currently working as a senior data scientist at PepsiCo, and I did my masters in artificial intelligence from University of Hyderabad back in 2013. I had a total of 11 plus years of experience working in data science, machine learning, and artificial intelligence, and I have implemented projects in multiple industries ranging from retail, healthcare, manufacturing, banking, and finance sectors. So, based on all my experience and my expertise, I'm going to present this today. So, my topic title is Democratizing Enterprise AI, how AutoML is transforming predictive analytics with 60 to 80% faster development. Before understanding this AutoML, in olden days, we were using different machine learning models and different hyperparameter configurations. And it is taking more time. Whenever you take any problem, and if we have to develop a predictive analytics solution, being it classification, regression, or clustering, we have multiple machine learning models, and each algorithm has a number of hyperparameters, and each hyperparameter takes many different values. Building multiple models and tuning those multiple hyperparameters, and coming up with the best model takes a lot of time. But with the advent of these AutoML techniques, there is a paradigm shift in the way that machine learning engineers or data scientists are developing these machine learning models for different problems that they are working on. So these are the main advantages of AutoML techniques. So this AutoML techniques encompasses and the tools that automate traditionally manual expertise dependent processes, from data pre-processing and feature engineering to algorithm selection and hyperparameter optimization. Another advantage of using this AutoML is they bridge the talent gap. If you have to build different machine learning models, if without having this AutoML, you need to hire a machine learning engineer or data scientist to build these different models and to come up with a solution. But by using these AutoML techniques, you can effectively bridge the talent gap that has constrained many organizations' analytical capabilities, enabling business analysts and domain experts to develop predictive models without extensive programming expertise. So these are the evolving capabilities. As I said, early systems focused primarily on algorithmic selection and hyperparameter tuning, and the recent developments in the AutoML focuses not only on algorithmic selection and hyperparameter tuning, they also address the entire machine learning pipeline, including deployment and monitoring. So these are the theoretical foundations of AutoML. As we initially discussed in the previous slide, these are the common or basic foundations of AutoML. So one is the art. So this optimization theory employs various strategies to navigate where, as we discussed in the beginning of the session. So these machine learning models have different hyperparameter configurations, and each hyperparameter has multiple values. So this is related to this optimization theory. So what algorithm to use and what hyperparameter to tune and what are the best values for those hyperparameters comes under this optimization theory. And the second foundation for AutoML is the meta learning. So this meta learning includes how to learn across data sets and modeling tasks. Modeling tasks here, it can be regression, classification, or clustering. And how do we train multiple models to come up with the best model to use it in the real time. And the next third foundation for this AutoML is the computational efficiency. Balancing exploration and exploitation during the model training comes under this computational efficiency. So we should not focus only on the exploration or only on the exploitation. So we have to do a balance between the exploration and exploitation while training these machine learning models. So these AutoML systems leverage these foundations to efficiently identify promising solutions while transferring knowledge between problems. They employ techniques such as Bayesian optimization, genetic algorithms, and gradient-based approaches to navigate the complex space of possible model configurations significantly, and also they significantly improve the efficiency and performance of traditional systems. So this is how the AutoML frameworks have been evolved. So it initially started with AutoVeca, which was introduced in 2013. So this AutoVeca pioneered combined algorithmic selection and hyperparameter optimization, and it established the foundation of subsequent AutoML frameworks. This is the first in the AutoML frameworks or AutoML techniques, which was introduced by AutoMaker. And then it followed by AutoScaler. So this AutoScaler not only involves hyperparameter optimization and algorithmic selection, it also introduced the transfer learning concept. So what does it mean by transfer learning is, so the any model or algorithm that was trained on one task can be used to retrain on another task. We can take an example of any deep learning models or image recognition models. So the models that were trained to identify cats and dogs can be used to retrain from last couple of layers to identify other things, other animals like horses or any other animals. So this comes under transfer learning. And nowadays there are more advanced AutoML frameworks are coming up into the market. They not only focus on hyperparameter optimization and algorithmic selection, they also focus on data preprocessing and other data preparation and other techniques. Some of the notable players in this end-to-end platforms are Google Cloud AutoML and H2O.ai's driverless AI, and they extend automation across the entire ML lifecycle. This is an extension to the previous slide. These are the prominent AutoML framework analysis. Now I am comparing the differences between AutoVeca, IBM's Auto AI, and Microsoft's NI. As we discussed in the previous slide, AutoVeca was introduced in 2013, and it focuses mostly on the algorithmic selection and hyperparameter tuning. And the technique is called the sequential model-based algorithmic configuration, and it uses Bayesian optimization to navigate these complex set spaces. And in 2023, KDD has awarded AutoVeca as a test time award in 2023. IBM's next one is IBM's Auto AI. It extends traditional capabilities by addressing the entire machine learning lifecycle within enterprise context. It also includes automated data preparation, feature engineering, model selection, and hyperparameter optimization. The main difference with respect to IBM's Auto AI is it has a strong integration with IBM's Watson ecosystem, and it enterprise-focused features like built-in fairness checks and explainability tools. The third one in this comparison is the Microsoft's NNI. It takes a specialized approach focusing on neural network optimization and automated deep learning. It provides infrastructure and a neural architecture such hyperparameter tuning and model compression through a highly modular framework. It also supports major deep learning frameworks such as TensorFlow, PyTorch, etc. It offers flexible deployment options across diverse computing environments. This is the framework comparison strengths and limitations. These are the different strengths and limitations of the three frameworks that we have discussed: AutoVeca, IBM's Auto AI, and Microsoft NI. Let us first start with the AutoVeca. So the primary strength of AutoVeca is in pioneering cache solution, and it also integrates with established ML toolkit, and it has a strong academic foundation. And the key limitations with AutoVeca is it has a limited end-to-end automation. It has less support for deep learning, minimal enterprise integration features. And the best enterprise use cases for using AutoVeca is academic research for developing proof of concept projects. And it will be suitable for organizations with existing Veka investments. The next one is Auto AI, which is from IBM. The primary strength of Auto AI from IBM is its end-to-end ML lifecycle automation, built-in fairness, and explainability tools strong, and it has a strong enterprise integration. The key limitations, it can be limitation for some of the users. We will have a vendor lock-in with IBM, and it's a proprietary ecosystem. It may be expensive for some clients, and it is higher implementation complexity. The complexity of implementing IBM's Auto AI is difficult. And the best enterprise use case for IBM's Auto AI is regulated industries like finance and healthcare, organizations with existing IBM infrastructure application requiring explainability. The third one in this comparison is NI from Microsoft. The primary strengths of an NI is its deep learning specialization, multi-framework support, flexible deployment options. And the key limitations, it has a steeper learning curve, less focus on classical ML algorithms, and requires more technical expertise. Best enterprise use cases are deep learning applications, optimizations with teams with strong technical capabilities. These are the enterprise integration considerations. So IT infrastructure integration. Organizations must evaluate compatibility with current data, current storage solutions, processing frameworks, and more, and model deployment infrastructure. API-based integration approaches have emerged as preferred pattern, allowing AutoML systems to interact with existing data pipelines while minimizing disruption. And these are the deployment options. And cloud-based deployments offer scalability, but may introduce data movement challenges. So when you have to implement a solution in the cloud-based infrastructure, you may have to move your data from in-house systems to cloud-based systems, which comes with some cost and time. On-premises implementations provide greater control, but require significant computational resources. And the middle ground, the hybrid approach, leveraging containerization and orchestration technologies, present a promising middle ground. Data governance requirements, robust mechanisms for data quality assessment, version control, lineage tracking, and access control are essential. AutoML systems typically require substantial volumes of training data, amplifying the importance of governance frameworks that ensure data accuracy and appropriate uses. Organizational adoption for AutoML. Traditional boundaries between engineering, data science, and business analysis roles often blur as AutoML democratizes model development capabilities. And these AutoML establishes cross-functional governance. Successful implementations typically establish cross-functional teams responsible for model governance with clearly defined hands-off between automated and human-led processes. Implement change management, address potential resistance from technical specialists by encouraging responsible adoption by business users through targeted training and communication. Create tiered approaches. Many organizations implement tiered approaches where straightforward predictive tasks leverage AutoML, while complex mission-critical applications maintain greater human oversight. These are the enterprise benefits of using AutoML. 60 to 80% of the development time will be reduced by using these AutoML techniques or strategies, and there will be a return on investment within 12 to 18 months of adopting these AutoML strategies, and there will be 30% reduction in downtime when using these AutoML strategies or techniques. Democratization of predictive analytics. The first one is expanded access. AutoML enables business analysts, domain experts, and non-specialists to develop sophisticated predictive models with less machine learning knowledge. Breaking down silos allows those closest to business problems to directly engage in solution development. Citizen data science. Many enterprises establish citizen data scientist programs with AutoML as the technological foundation. Multiplied capabilities. Effectively multiplies analytical capabilities without proportional increases in specialized hiring. These are the implementation challenges. Interpretability concerns. Automated approaches often generate complex models resistant to straightforward human understanding. Data quality dependencies. AutoML systems remain fundamentally dependent on data quality, potentially amplifying underlying issues. Domain-specific requirements. Generic solutions often struggle with highly specialized domain problems requiring industry-specific approaches. Technical accumulation. Unmanaged adoption can accelerate technical debt through model proliferation without adequate governance. These are some of the strategies to overcome those challenges. Implement explainable AI, address data quality, enable domain customization. So the first one is implement explainable AI. So integrate explainable AI techniques alongside AutoML, establish interpretability thresholds for different application categories, and maintain simpler model adoption for high transparency requirements. Address data quality. Implement systematic data quality assessment prior to AutoML deployment. Automated data quality monitoring layer processes for handling quality exceptions and realistic expectation setting. Establish data quality thresholds that must be satisfied before automated modeling proceeds. Enable domain customization. Develop customized AutoML frameworks that incorporate domain knowledge via specialized preprocessing pipelines, custom algorithm implementations, domain-specific objective functions, and expert-guided constraints on model exploration. These are the future directions for using AutoML. Explainable AI integration. Next generation AutoML frameworks are incorporating explainability by design rather than as an afterthought. This includes optimization objectives that balance predictive performance with interpretability metrics and automated generation of explanation artifacts. Edge computing applications. AutoML systems specifically designed to optimize models for edge development. Considering resource constraints, power limitations, and specialized hardware accelerators, these systems automatically balance model complexity against inference speed and memory footprint. Federated approaches converging with AutoML to address data privacy and sovereignty challenges, enabling predictive model development across decentralized data sources without requiring data centralization. Regulatory aware AutoML. Evolving regulatory frameworks are driving innovation in automated compliance verification and documentation generation, with systems incorporating regulatory awareness directly into optimization objectives. Enterprise implementation roadmap. Assessment and planning. Identify high value use cases, evaluate data readiness, select appropriate framework, and define governance structure. Success metrics include prioritize use case portfolio and established success criteria. Common challenges include unrealistic expectations and insufficient data quality assessment. Initial implementation. Deploy AutoML for targeted use cases, establish and monitoring and evaluation, train initial user cohort, and document early learnings. Success metrics include model performance metrics and development time reduction. Challenges include technical integration issues and resistance from data scientists. Scaling and optimization. Expand use case governance, enhance governance frameworks, establish model ops practices, and integrate with business processes. Success metrics include enterprise-wide model inventory and business impact measurements. Challenges include model proliferation and technical debt accumulation. Advanced integration. Incorporate emerging AutoML capabilities, integrate with complementary AI systems, and develop custom domain adoptions. and establish continuous improvement cycles. Success metrics include hybrid AI system effectiveness and competitive differentiation metrics. Strategic recommendations for enterprise adoption. We have to first start with phased implementation and then proceed with balanced governance model, strategic workforce, integration with use case boundaries. Organizations should adopt phased implementation approaches that balance ambition with paradigm. Initial deployment should target well-defined use cases with clear success criteria and moderate complexity. Effective governance structures typically combine centralized oversight with distributed execution capabilities. Thank you.